Okay, so welcome to section 5.2. Now, this section takes quite a bit of a turn from what we were just doing. So we're not going to be working on any antiderivatives in this section, and we're actually going to be talking about the concept of area, which might seem completely unrelated. But by the time we get to section 5.3 and 5.4, and we talk about what's known as the fundamental theorem of calculus, you'll see how the concept of area and the concept of this integration process really go hand in hand. And so just like before, when we talked about derivatives and we said that derivatives dealt with slope, integrals are essentially going to be dealing with area, but those are going to be what we call definite integrals, and we'll get to that. So right now, we're just going to do a quick review of sigma notation, and then in some later videos in this section, we'll talk about how area is going to be involved with those sigma notation problems. So here is the sigma notation for the sum of n terms, a1 plus a2 plus a3, etc. You can see that in this notation here, you've got a few different things. You've got I equals 1 on the bottom. I is known as the index of summation, so this can be any variable whatsoever, but typically whatever variable this is down here is the same variable that you would see in here. And so what we do with sigma notation is we start down here, we plug this number in, and we would get a1. And then this means let's continue to do this, taking the sum where we plug in subsequent values of this and continue to add up the result until we get to n, or actually after we use I equals n. So this would be, a1, and then you would go plus a2 plus a3 plus a4 all the way up to the last one, which would be a sub n. And so if you look at some examples down here, this is exactly what we're doing. So the summation of I plus 2, where I is going from 1 to 5, I'm literally going to plug in 1, so it's going to be 1 plus 2 plus, now I'm going to plug in 2 plus 2 plus, and that's going to continue until we end up with, we'll have I equals 4, then I equals 5, so the last one's going to be 5 plus 2. So you can see that this is just going to be 3 plus 4 plus 5 plus 6 plus 7. That's what our answer is, 3 plus 4 plus 5 plus 6 plus 7. And so that's going to be 10 and another 10, so that's 25 for the total there. Or this problem, j is equal to 4, and we're doing the sum of j cubed, and we're going all the way up to j is equal to 7. By the way, this is called the lower bound. I don't think I mentioned that. This is called the upper bound up here. So my lower bound is 4, so my first evaluation is 4 cubed, and then we have 5 cubed, 6 cubed, and then 7 cubed. And then I would stop. And when you put this all into the calculator and you add it up, you're going to get 748. And so there's some summation formulas and properties that we really need to be familiar with, since we're going to be working with the sigma notation a ton. And so let's take a look at those right now. And so the first one is, if you do the sum of a constant times a sub I, and we can even think about this one before I even just tell you what the formula is. If you plugged in 1 and then 2 and then 3, you would have Ka1 plus Ka2 plus Ka3 plus Ka4, etc. And so you're going to have K as a factor of all of those terms. So if you wanted to, you could just take that K out and factor it out before you even start. And so this is almost like the constant multiple rule that we saw with derivatives, and we actually also saw it in the previous section with indefinite integrals. So whenever you have a constant, you're doing the sum of a constant times a function, you could pull that constant out in front. Likewise, whenever you're doing the sum of a sum or the sum of a difference, we can actually break this up and say that this is equal to sigma of a sub I, where I is going from 1 to n, plus or minus sigma of b sub I, where I is going from 1 to n. So the sum of a sum is the sum of the sums. That sounds really weird, but you can break this up. Or the sum of a difference ends up being the difference of the individual sums. Okay, that might be weird, but just know that you can break this up the exact same way that we kind of broke up things when we did indefinite integrals individually. You know how we would do one term at a time, or when we did derivatives, we would do the derivative of one term at a time. So this is basically saying you could do the sum of one term at a time. And then here's a few others, like if you take the sum of a constant where I is going from 1 to n, this constant's not changing and it's not really impacted by this, but what you'll have is the result will be this constant will be produced the number of times that you actually run through this index. So if I goes from 1 to n, you're going to end up with producing this constant c n times. So the answer to this is it's quite literally just the constant times n. And then these are a couple of really common sums that we see a lot. This is the sum of the first n natural numbers, the sum of 1 plus 2 plus 3 all the way up to n. That is actually equal to n times n plus 1 divided by 2. And then this sum, the sum of 1 squared plus 2 squared plus 3 squared, etc., is equal to n times n plus 1 times 2n plus 1 divided by 6. And these formulas and properties are very handy when working with some examples. So take a look at these couple of examples right here. So I can actually evaluate this instead of just plugging 1 in and then 2 and then 3 and plugging 10 values in and taking forever to punch that into the calculator and get an answer. I can do the following. I could say that this is the sum of I squared, where I is going from 1 to 10, minus the sum of 1, where I is going from 1 to 10. Now I can use the formula for the sum of I squared. We saw that one right up here. So that's going to be equal to n times n plus 1 times 2n plus 1 over 6. But notice that my n is going to be 10 in this case. And so this formula translates to 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. And then minus, this is a constant. And so this is actually this property right here. The sum of a constant that many times is the constant times n. So that's going to be our setup, and this will be 10 times 11 times 21 divided by 6, and then you subtract 10. If you go over here and you put this into the calculator, I'm just going to save us the time, you get 375. But the nice thing is, look how quickly we're able to get to that answer using the properties, and I didn't have to bother with plugging this in one thing at a time. And so with this one, it would look like this. You would say, well, this is the sum of 2i, where I is going from 1 to 15, minus the sum of 3, where I is going from 1 to 15. And there's a constant. I'm going to pull that out. So this is 2 times the sum of I, as I goes from 1 to 15, minus the sum of a constant 15 times. So that's going to be minus 3 times 15. That's applying this concept again. The sum of a constant n times is that constant times n. And then this piece right here becomes 2 times, so this is the sum of I, 15 times, or the sum of I, where I is going from 1 to 15. And that's going to be n times n plus 1 divided by 2. And then we have that minus 45, and so the 2's cancel. And we end up with 15 times 16 minus 45, and that leads us to an answer of 195. And I will tell you that, this is a much easier way than going through and plugging things in one at a time. You're really not going to do a lot of this right here, because the reality is we can do this in the calculator, and I'm going to show you how we can do this in the calculator right here. So some of our calculators might have different formats, but what I'm going to do is the following. I'm going to go into sum, a sequence, and sum and sequence are both under second stat. That's in the list menu. One is number 5 under ops and the other is number 5 under math. And so let's do this first example, the sum of I squared minus 1, where I goes from 1 to 10. So I'm going to say second, what did I say, second? This is under second stat. There we go. And we are going to go over to math. Sum is number 5. So we're going to sum, again, second stat, over to ops. Sequence is number 5. And some of your calculators won't have this set up. You'll actually need to plug in the following. You'll need to plug in the function, you know, comma x, comma your lower bound, comma your upper bound, and then comma 1. But that's exactly what this information is doing. So the first thing is our expression, or our equation. So if our equation is I squared minus 1, I'm just going to call it x squared minus 1. And then variable is x, start was 1, end was 10, and step is always going to be 1 when using sigma notation. So you click paste, and so some of you are going to actually have to enter exactly as you see this right here. But you press enter, and there it is. You get 375. So I probably got 375 through the calculator as quickly as I did this way, and so that's kind of speaks to the usefulness of these properties and formulas. But obviously, if you can rely on the calculator, then rely on the calculator when you can. Okay, so one other initial example right now with sequences, and then what we'll do is we'll jump into how areas tie into this in the next video. So this last example that we're going to look at in this one is sometimes you're going to have to take your patterns that have been revealed and condense them into sigma notation. So you're going to see this with the area videos coming up. When you have a pattern like this, you say, oh, well, there's only a small change each time, and at first you could see when you have this expression 1 minus 1/4 squared, there's a 1 right here, and then it becomes a 2/4 squared, and then a 3/4 squared, up to a 9/4 squared. Notice that we're adding all of these, and so this is nothing more than the sigma notation of, we could say 1 minus I/4 squared, where I is going from what to what? Well, the very first value of I that we have is 1, and the very last value is 9. So I is going from 1 to 9. And so that's just a nice way to condense something like this. And when we see those patterns in math, a lot of times we try to abbreviate. And the nice thing is now we know if we have this abbreviated, we can plug this into the calculator and quickly evaluate this whole thing also. Okay, so let's continue with the notes and the area concept in the very next video.